Picture a star, not a pinprick of light, an actual star, roaring, burning, 5 times the size of everything our sun will ever be. It's been alive for billions of years, just sitting there, doing what stars do. And then something notices it. Something with no light, no shape, no sound, just pull. The star doesn't know, it can't. There's no alarm, no warning flash, no last second to react. In the next few hours, this star stops being a star. It becomes a thread, a glowing, screaming thread of plasma, millions of miles long, unraveling into nothing. We're going somewhere dark today. Not dark like a horror movie. Dark like the universe doesn't care that you exist. Dark to the edges of black holes, to one of the most violent, most visually spectacular things that can happen in the cosmos. A moment when physics stops being theory and becomes the most extreme destruction you'll ever try to wrap your mind around. Okay, I'm going to start somewhere you absolutely did not expect. The beach. Stay with me. You've watched tides your whole life. Water comes in, water goes out, regular as breathing. You probably know the moon has something to do with it, but here's where most people stop thinking and where it actually gets interesting. The moon doesn't just pull on the ocean, it pulls on everything, the whole earth, every molecule of it. But, and this is the part that matters, it doesn't pull on everything equally. The side of Earth facing the moon pulled harder, the side facing away pulled weaker. That difference, that tiny persistent gap in pull strength, that's called a tidal force. Think about it this way. You're in a tug of war, except someone's pulling your head one way and your feet just slightly less. You'd feel it, that uncomfortable, elastic stretch. That's a tidal force. On Earth, it's gentle enough to slosh oceans around. Nothing dramatic, nothing scary. But near a black hole, tidal forces don't slosh water. They don't bend, they don't nudge, they rip. We're talking about a force so unequal, so grotesquely extreme, that it can reach out across millions of kilometers, grab a star 1,000,000 times heavier than Earth, and stretch it, like taffy, into a thread of glowing plasma, in hours, not centuries, hours. That's spaghettification. And here's what I need you to sit with for a second. This isn't a simulation. This isn't what we think might happen. Astronomers have pointed real telescopes at real galaxies and watched it happen, in real time. And what they saw was so strange, so beautiful, and so deeply violent. It changed how we understand the universe kills things. But before we get there, we need to go deeper. Because the real question isn't what is spaghettification. The real question is, why does it happen at all? What makes a black hole so fundamentally different from every other thing in space? It comes down to one word, one concept everyone learned in school, and almost no one thinks about hard enough: gravity. In 1687, Isaac Newton handed humanity something extraordinary. He said, every object with mass pulls on every other object with mass. Every single one, all the time. The bigger the mass, the stronger the pull. The closer you are, the stronger the pull. Simple. Almost embarrassingly simple, but it worked. That one equation predicted planetary orbits, steered spacecraft, explained the tides. For 300 years, Newton's gravity was the law. until Einstein sat down and broke everything. Einstein said, "Wait, gravity isn't a force at all. It's a shape. Mass bends the fabric of space and time around it. Like a bowling ball sitting on a rubber sheet, everything nearby rolls toward the dip. That's what we call gravity, not a push or a pull, a curvature. So a planet? Gentle curve. A neutron star? A steep, vertiginous slope. A black hole? A black hole punches straight through the sheet. At its center, a singularity, a point of infinite density where the math just stops, where our best equations throw up their hands and say we don't know. The universe pulls a curtain. We're not allowed to see past it. And that should bother you. It bothers physicists. It's been bothering them for 100 years. Now, size matters here. A lot. Stellar black holes are the small ones, formed when massive stars collapse, 5 to 100 times the mass of our sun. Then there's the middle tier, intermediate black holes, hundreds of thousands of solar masses. And then there are the things at the center of galaxies, the ones that make the word massive feel inadequate. Supermassive black holes, millions to billions of solar masses. The one at the heart of our own Milky Way, Sagittarius A star, is 4 million times the mass of our sun, and that's not even the biggest one we know about. Now, here's where this gets genuinely weird and important. The size of the black hole completely changes the outcome when a star falls toward it. This is where most videos skip ahead, but trust me, you want to understand this part. It's called the Roche Limit. Every star, including our sun, holds itself together through its own gravity. Nuclear fusion pushes out from the core. The star's mass pulls everything inward. It's a tug of war. The star wins every single day for billions of years. But here's the catch. The closer a star gets to a black hole, the harder the tidal force pulls on its near side versus its far side. And at one specific distance, one line in the dark, those tidal forces finally overpower the star's self-gravity. That line is the Roche Limit. Cross it, and the war is over. The star has already lost. It just doesn't know it yet. But here's the twist most people miss, and this changes everything. Whether spaghettification actually happens where we can see it, that depends on one thing: whether the Roche Limit sits inside or outside the event horizon. For the absolute monsters, black holes of hundreds of millions of solar masses, the event horizon is so vast, it swallows the Roche Limit whole, which means a star can cross the point of no return and still be completely intact. No fireworks, no debris. The black hole just eats it whole, one gulp, gone. But for black holes between roughly 1 million and 100 million solar masses, the Roche Limit sits outside the event horizon. And that gap is where the show happens. That's where a star gets torn apart in full view, where it lights up the sky so violently it briefly outshines the entire galaxy around it. That's where we get to watch. Okay, I want to take you through this, the whole thing, start to finish, the actual death of a star, not simplified, not sanitized, the real sequence, because once you see it, you won't be able to close your eyes to what's out there. Our star has been burning for maybe 5 billion years, born from a cloud of hydrogen that collapsed under its own weight. A nuclear furnace that's been quietly, steadily fighting gravity every second of its existence. But it's made a mistake, or rather, the universe made one for it. The galactic core is a terrible neighborhood. Millions of stars packed close together, all orbiting the same monstrous center, and sometimes two stars drift too close to each other. Their gravity nudges, redirects, and just like that, one of them gets sent down a different path. The star doesn't feel it, not for thousands of years. It just drifts, slowly, on its new trajectory, getting closer to the center, millimeter by gravitational millimeter, until one day, it's close enough for the black hole to finally start pulling back. The tides change first. The side of the star facing the black hole starts getting pulled just a fraction harder. The star's equator bulges, stretches slightly outward, like someone pressing a thumb into a rubber ball. The star's own gravity is still fighting, still holding, but the gap is narrowing. Every second it gets closer, the tidal forces get stronger, exponentially stronger. That's the cruel math of gravity. And then the star crosses the Roche limit. What happens in the next few hours is one of those things where language genuinely fails. I'll try anyway. The near side of the star, the side facing the black hole, is now being pulled so much harder than the far side that the star's own gravity simply cannot compensate. The star doesn't explode, it doesn't shatter, it elongates. The near side accelerates forward, the far side lags behind. The whole structure, billions of years of stable nuclear burning, begins to unravel like a thread being pulled from a sweater. What's left is called a debris stream, a strand of plasma, mostly hydrogen and helium, moving at a significant fraction of the speed of light, glowing at tens of thousands of degrees, and it's moving in two directions at the same time. Roughly half the star's mass, the outer part, gets flung away. It escapes into the cosmos, gone forever. But the inner half, that half, gets captured. It wraps around the black hole and starts falling back in. And when those streams of debris collide with each other, they release enormous amounts of energy as heat. The debris flattens, circularizes, and begins forming something called an accretion disk. This disk, this funeral pyre built from what was once a living star, becomes one of the brightest objects in the universe. For weeks, sometimes months, it radiates X-rays, ultraviolet light, and visible light simultaneously. So much energy that it can briefly outshine every single star in its host galaxy, combined. A galaxy with 400 billion stars, all drowned out by the death of one. Astronomers have a name for it, a tidal disruption event, a TDE. And here's what I really want you to get. We haven't just theorized these, we haven't just modeled them, we've watched them, with real equipment, pointed at real galaxies, catching real photons of light that spent millions of years crossing the void just to reach our detectors. The first solid TDE detections started showing up in the 90s, flares at galaxy cores that didn't fit any known star-forming pattern. Astronomers started building a case. Then in 2014, a sharper event, ASAS N14 Li, roughly 290 million light-years away. Telescopes caught a months-long X-ray flare, detailed enough to watch the debris actually fall toward the black hole, to study how a monster feeds. It was fascinating, unprecedented, but it was 2019 that changed everything. The Zwicky Transient Facility, an automated sky survey that scans for things that change, picked up a new optical flare in a galaxy called 2 masks J0446 3790 1013 349. They tagged it ET 2019 QIS. Within days, astronomers were piling on optical telescopes, X-ray observatories, ultraviolet instruments, all aimed at the same small patch of sky. What made AT 2019 Keys different from everything before it? They caught it early, almost shockingly early, before the accretion disk had even fully formed. For the first time in history, they watched the whole thing. The approach, the disruption, the debris stream, the disk forming, the flare rising, then slowly fading, start to finish. They watched a star die. The numbers, even now, are hard to make feel real. The stellar debris expanded at about 10,000 kilometers per second, 3% the speed of light. The flare peaked about 40 days after disruption. The disrupted star was roughly half the mass of our sun. The black hole at the center, about 1 million solar masses, perfectly placed in exactly the right mass range for spaghettification to happen outside the event horizon. Perfectly placed to be seen. Can I step back for a second? Because there's something in this that science doesn't usually stop to say out loud. That star had a history. It was born, maybe 5 billion years ago, from a cloud of collapsing gas. It spent its whole life in a kind of perfect equilibrium, burning quietly in the dark. It may have had planets. Maybe one of them had liquid water on its surface. Maybe some of that water had chemistry complex enough to spark something. We'll never know, because in a handful of hours, in what amounts to a rounding error in cosmic time, it was undone, stretched into glowing gas, fed to a gravitational drain we still don't fully understand, and the universe didn't flinch. Stars die at around 2 per second across the observable universe. 2 per second. TDEs happen once every 10 to 100,000 years in any given galaxy. There are 2 trillion galaxies in the observable universe. So right now, while you're watching this, somewhere out there, a star is crossing the Roche limit. The debris stream is forming. The accretion disk is lighting up. Right now. It's happening right now. But here's the thing that quietly floors me when I sit with this. We know, we tiny, short-lived, fragile humans on a rock in a forgotten corner of the galaxy, we figured this out. We built instruments sensitive enough to catch a flash of light from 215 million light-years away. We decoded the physics of what caused it. We timed the debris stream. We mapped the disk. Whew. We understood something that the universe didn't intend for anyone to witness. That's not a small thing. That might be the most remarkable thing our species has ever done. Now, you're probably wondering about us, about Earth, about our sun. Could this happen here? No. Not this way. Our sun is 26,000 light-years from the galactic core. Its orbit is stable. Sagittarius A star isn't going to reach out and grab us. We're fine in that very specific sense. But our sun is still going to die. In about 5 billion years, it runs out of hydrogen. It swells into a red giant, large enough to engulf Mercury, Venus, and probably Earth. Then it sheds its outer layers into space in a soft luminous cloud, and what's left collapses into a cold white dwarf. Compared to being spaghettified by a black hole, honestly, it's almost gentle. But here's what matters. Even in that quiet death, something continues. The oxygen and carbon and neon that our sun spent billions of years forging, it scatters into space, into nebulae, into the raw material of new solar systems, maybe into the atmosphere of a new world, maybe into the chemistry of something alive. Stars die, but atoms don't. And even in spaghettification, even in that, the material that was a star doesn't vanish. Half of it escapes into the cosmos. The other half, after forming that blazing accretion disk, some falls inward, some gets launched as jets, relativistic jets, beams of matter and energy that lance across entire galaxies at close to the speed of light, traveling for millions of years, carrying the atoms of a dead star to parts of the universe that may never have seen those elements before. Even the most violent death in the cosmos is also, in some strange cold way, a delivery. Here's the honest truth. For all we know, and we know a lot, spaghettification still has secrets we haven't cracked. Real, stubborn questions that our best physics hasn't answered yet. Why do some TDEs produce powerful relativistic jets and others don't? Is there a trigger? A threshold? Is it spin? Is it the star's mass? We don't know. What happens to the half of the star that escapes? Does it eventually form new structures? Wander the galaxy for billions of years? Seed a molecular cloud somewhere? We don't know. And the hardest one, what happens to the material that actually crosses the event horizon? We can model the disk, we can observe the jets, but past that threshold, we're blind. Our equations break, our theories contradict each other. The universe has not given us that page yet. But the next decade is going to be wild. The Vera Rubin Observatory, coming fully online, will survey the entire visible sky every 3 nights, not catching a handful of TDEs a year, potentially thousands, each one a new data point, a new piece of the puzzle. And then there's LISA, the Laser Interferometer Space Antenna, 3 spacecraft a million kilometers apart, listening for ripples in space-time itself. When a stellar object spirals into a supermassive black hole, it creates gravitational waves, actual distortions in the fabric of space. LISA, launching in 2035, is designed to detect them. We won't just see TDEs anymore, we'll feel the space-time around them shiver. Spaghettification isn't just a spectacular death, it's a tool. The most extreme physics lab the universe offers us. It pushes Einstein's general relativity into territory we couldn't manufacture on Earth in a billion years. Every TDE we observe is a data point, a clue, a page in a textbook that the universe is writing, and we're only just learning to read. So, the next time you look up at those quiet, steady points of light, remember they're not permanent, not safe. Every star you see has a fate. Most will die gently, some will explode, and a few, the ones with the wrong trajectory in the wrong galaxy, will drift too close. And in the span of a few hours, a billion years of stellar life will be pulled thin, stretched into light, swallowed. Spaghettification, nature at its most brutal, and somehow at its most honest. The universe doesn't play favorites, it doesn't spare the brightest stars, it just pulls. If the universe feels a little bigger and a little stranger right now, good. That's exactly what this is for. Drop your biggest black hole question in the comments. I genuinely read them. Some of our best video ideas have come from down there. And if there's a topic you want us to pull apart next, tell me. This channel goes where you want it to go. If you're not subscribed yet, now's the time. Every week we go somewhere most people never think to look. Stay curious.